Okay. All right, so welcome, gentlemen. I'm just giving it a moment to get my confirmation. So hopefully my image is being pushed properly. Just give it a moment. Yeah, it's looking good. All right. If I see that slide away. Just giving it a moment to get my confirmation. So hopefully my image is being pushed properly. Uh-oh. The audio's pushing. It looks like it's frozen though. Oh, come on. Okay. Yeah, because I don't think you guys can see. I don't think you can see my screen. Yeah, it's weird. Like I don't understand why it does that. Okay, let me just all I can do is like start and stop the screen, the image again. Okay, stop the screen share. Start the screen share. Maybe maybe YouTube has to be open for it to work better. Because I tried to do it before you guys in here and it was looking good, but then lo and behold, it just froze. I should see my desktop. Start this. Maybe YouTube has to be open for it to work better. Because I tried to do it before you guys in here and it was looking good. Okay, I'm going to go with it. I can see my desktop, and I'll get the second wave of students in about 10 minutes. All right. So usual operations. So we are at the end of week 7, right, gentlemen? Okay, we're at the end of week 7. Uh-oh. Let me see. And I'll get the second wave of students. Yeah, I think it's okay. Okay, it's looking good. So, all right. No real announcements. We're just gonna kind of keep plugging and chugging like normal. The only thing that's a little bit different is today is going to be the last day that we more than likely need to do 2 sections a day. So today we're going to be focusing on 3.3 and 3.4. But going forward, we should only have to do like 1 section per session. Okay. As usual, if you have questions, feel free to unmute yourself to get my attention. And so let's see. So let's start with section 3.3. Let's go like this. Okay. Save view. How does it look like that? Okay. So we're continuing chapter 3 of applications of differentiation. So we're just really still talking about derivatives. Okay. And with this section, we're going to be continuing our discussion on graph sketching. So using derivatives and sketching graphs of curves, right? So you still, all the rules from college algebra still apply. We don't have too much pre-calculus in here, but there's a lot of algebra, college algebra, stuff like that. So we'll be looking at asymptotes and rational functions. A few objectives here. Let me minimize this. Okay. Objectives, we like to find limits involving infinity, determine the asymptotes of a function's graph, and graph rational functions. So this definition 1, a rational function is a function that can be a function f that can be described as follows. F of x is going to be some p of x over q of x, where p and q are polynomials, with q not the zero polynomial. The domain of f consists of all real numbers that as long as x does not make the denominator 0. Sorry, I'm still getting a little bit slow here. Okay. So the line x equals a is a vertical asymptote if any of the following statements are true. All right. So the limit as x approaches a coming from the left of f of x goes to positive infinity. The limit as x approaches a from the left of f of x goes to negative infinity. The limit as x approaches a from the right of f of x goes to positive, or the limit as x approaches a from the right goes to negative infinity, right? So as x gets closer and closer to some number, if our y goes to either positive or negative infinity, then that's how we identify a vertical asymptote, right? So the graph of a rational function never crosses a vertical asymptote if the expression that defines the rational function f is simplified, meaning that it has no common factors other than -1 or 1. Then if an input that makes the denominator 0, the line x equals a is a vertical asymptote, right? So given a rational function, after we simplify, as long as that expression, long story short, any x that makes the denominator 0 makes a vertical asymptote, provided that it does not also make a 0 in the numerator, right? If you have an x value and it gives you 0 over 0, 0 over 0 is not a vertical asymptote, it's a hole in the graph, okay? So given this example, determine the vertical asymptotes of the following function given by this, right? Okay, so essentially it's any x that makes the denominator 0 as long as it doesn't also make the numerator 0, right? So if we set the denominator to 0 and solve, basically you set each factor to 0, so it's gonna be, when you set each one to 0 and solve, you're gonna get x equals 0, x equals 1, and x equals -1. Okay, but the caveat is, notice that when you plug in 0, it gives you a 0 on top and 0 on bottom. So that's not gonna be a vertical asymptote, that's actually gonna be a hole in the graph. So this guy's gonna be a hole in the graph. So the plus or -1, right? That's supposed to be a -1. So those are our vertical asymptotes for this one, okay? Again, if anything is not clear, just feel free to unmute yourself to get my attention and we can talk about it. That looks good, let's copy. Go ahead.
Professor,
Yes.
how do you get the vertical asymptotes of x equals 1 and -1?
So I set the denominator equal to 0, right? So if we say x, well, first we should really simplify it, right? If we simplify it first, cancel our like factors, so this x is going to cancel this guy. Remember, we can cancel factors. Factors are things that we multiply or divide. Those can cancel. But if we're adding and subtracting, we can't cancel those, right? So those x's cancel. So then when we set the denominator equal to 0 and solve, we're going to have this x minus 1 times x plus 1 equals 0. So then by the 0 factor property, when 2 or more things multiply to give you 0, you set each thing to 0 and solve. So you say x minus 1 equals 0 or x plus 1 equals 0. And that's where these results came from. If we were to look at this graph and plug in x equals 0, it's not going to be a vertical asymptote when x is 0. It's going to be a hole or a gap in the graph. Okay. On a graphing calculator, you wouldn't necessarily see the hole or a gap, but it wouldn't be defined when x is 0. And there's also not a vertical asymptote. We should have vertical asymptotes plus or minus -1 or plus or minus 1. I guess it's the same thing. Okay. Ho, ho, ho. Okay, and here's the type version, right? So, yeah, right? Same deal. Same thing we did. Quick check I leave as exercises for you all. We're still getting, I'll check attendance again in like 3 minutes. So we have this definition too. It says the line y equals b is a horizontal asymptote if either or both of the following limit statements are true. The limit as x goes off to -infinity equals some of f of x equals some number, or the limit as x goes off to +infinity of f of x equals some number, right? So as x goes off to either the far left or the far right, and y gets closer and closer to some number, then that's when we have a horizontal asymptote. Now I want to say from college algebra, to find if there is a horizontal asymptote, in order to find it, there are 3 rules that we have to test. We have to basically compare the degree of the numerator to the degree of the denominator. The first one says, if the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is going to be y equals 0. The second one is, if the degree of the numerator is equal to the degree of the denominator, then your horizontal asymptote is going to be the ratio of your leading coefficients. And then the third one is, if the degree of the numerator is larger than the degree of the denominator, no horizontal asymptote. All right, let's see what we got on the next slide, right? So it says the graph of a rational function may or may not cross a horizontal asymptote. Horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. The degree of a polynomial in one variable is the highest power of that variable, right? So this is basically reiterating what I literally just said in the previous. Those three rules. If the degree of the numerator is less than the degree of the denominator, then y equals 0. is your horizontal asymptote, basically the x-axis. If the degree of the numerator is equal to the degree of the denominator, then you take the ratio of the leading coefficients. If the degree of the numerator is greater than the degree of the denominator, no horizontal asymptote. Okay, so those three rules is kind of summarized here in this definition too. So here we're asked to determine the horizontal asymptote of this function given by this. Okay, so if we're talking about horizontal asymptotes, we basically just compare the degree of the numerator. Okay, now I think the text is going to do it a little bit different. We can take the limit. I'll try to do it the way I think they're going to do it. Now, from college algebra, right? We see the degree of the numerator is equal to the degree of the denominator. So we should already see that the horizontal asymptote is going to be y equals 3/2, the ratio of the leading coefficients, right? Now, if we wanted to use the limit definition, in this case, we can factor out x squared from all terms. So we're going to rewrite this guy. We're going to factor out x squared from all terms. Okay. So then if we do this, we'll get 3 plus, that becomes what? 2 over x. Okay. Minus 4 over x squared. And on bottom, we're going to have 2 minus 1 over x plus 1 over x squared, right? So notice this is equal to the above statement. So now what we want to do is take the limit as x goes to, we can go to positive infinity, and it'll be a similar argument for as x goes to negative infinity. So now, essentially what happens, this is just 1, right? This is just 1, okay? And now as x gets bigger and bigger and bigger, think about this. So what happens to each of these terms as the denominator gets infinitesimally bigger, right? So think about it. When x is 1, this term is 2. When x is 2, this term is 1. When x is 4, this term is 1/2. When x is 8, this is 1/4. X is 16, this is 1/8. So notice that as this denominator gets bigger and bigger and bigger, this term is getting closer and closer and closer to 0, right? So as we let x go to positive or negative infinity, all of these terms essentially go to 0. So whenever you have a fixed number over the infinitely expanded denominator, then in the long term, those behave like 0. So then ultimately, because of that, the limit as x goes to positive infinity or negative infinity, then we get, that's where the 3/2 come from. Okay, let me check on you guys in Zoom. Hopefully that made sense, right? So that was a alternate articulation other than the way we did it in college algebra. But you can do it the way it's done in college algebra. That's fine as well. Okay. Let's see, you guys are here. I really want to stop the image, but no. Okay, I'll just go with it. Let's see. But I'm worried if I stop the image, I won't be able to bring it back. Okay. I think I got him already. Yeah, he must have like got booted or something. Seems like he left again. I think him as well. And okay, here he is. Okay. All right. I got these guys, so I don't know what happened to him, but I'm not going to worry about it. Okay. He might be having like connection issues or something. Okay, moving along, right? So we get 3/2. Okay, right? So they factored out the x squared like we did, they cancel, and then they got an expression like this. Now you take the limit as x goes to positive or negative infinity. It's the same kind of argument. Now it says find the limit as absolute value of x gets larger and larger and larger. So in either case, right? Remember we said plus or minus? You still get the same thing in either case. So the horizontal asymptote is y equals negative. I mean, y equals 3/2. Okay. Quick check, I'll leave it as an exercise, and we have this definition. So it says a linear asymptote that is neither vertical. Let me see if I go like this. Feels better. That's fine. That's fine. A linear asymptote that is neither vertical nor horizontal is called a slant or oblique asymptote. For any rational function of the form f of x equals p over q, a slant asymptote occurs when the degree of the numerator is exactly one more than the degree of the denominator. A graph can cross a slant asymptote, right? So we have an additional case where if the degree of the numerator is larger than the degree of the denominator by 1 degree, then we have a slant asymptote. Okay. So here we're asked to find the slant asymptote. Okay. So for this, notice that the degree of the numerator is larger than the degree of the denominator by 1 degree. So we're going to have a slant asymptote. In order to find it, we're going to use polynomial division, right? We can either use synthetic division or polynomial long division. In this case, it looks like synthetic division would be easier to do here. So I'm going to use synthetic. We can use synthetic whenever we're dividing by a linear binomial, right? So synthetic division, first you take your 0, the denominator. In this case, it's going to be a 1. So we're going to put 1 in the chair. And then we need all the coefficients from the numerator, right? And we gotta fill in any missing degrees, right? So since it starts with degree 2, the first coefficient is 1. Notice that it skips over degree 1, so we have to do a placeholder of 0. And then the -4. Okay, so when we go to do synthetic division, the first term just comes down. Okay. On the diagonal, you multiply, so 1 times 1 is 1. Vertically, you add, so that's a 1. Diagonal, you multiply. Vertical, you add, and this is our remainder there, okay? So we started with the degree 2, so that means this is x plus 1, right? So when we say that numerator divided by the denominator, that's going to be the same as x plus 1 minus 3 over x minus 1. Let me see. Does it look weird? What am I missing? Oh, the remainder is, what is the remainder? Is that, okay. So the equation of our slant asymptote, right, is gonna be this guy here, right here. Basically this part right here. Let me think about it. Yeah. Yeah. It should just be the x plus 1, right? I think that's what it is. Y equals x plus 1. I'm not thinking about that incorrectly. Okay. So that should be the equation. Let's go with it. If it's not right, we'll fix it. But I think that's it. That's what it should be. So y equals x plus 1, and you see it there, right? Okay. So here's a type version. To find the slant asymptote, first divide the numerator by the denominator. Notice we got that remainder of -3. We got this guy here, right? So again, if we think about this in terms of x going to either positive or negative infinity, we have a fixed number over a really large number. So then this guy essentially goes to 0. And we're going to be left with this guy. So that's why the equation, so in the long term, it's going to get closer and closer to this. All right, as x goes to either positive or negative infinity. Okay, so you see it here. So now we see that as the absolute value of x gets very large, again, this guy approaches 0. We just said that. So for a very large absolute value of x, the expression is basically as x goes off to the far right or far left, it gets closer to this guy here. And so that's why we have y equals x plus 1. Okay. Okay, let me check on you guys in Zoom for a moment. Okay, you guys are looking good. Check the chat. Chat looks decent. Okay. Guess you guys are okay. I'm going to suppress that. Come on, go away. There we go. Okay. As usual, if you have questions, feel free to unmute yourself to get my attention. We can talk about it. Let's keep going. So quick check I leave as an exercise for you. Let me see the time. Okay, we're good. I think we got about 10 minutes left in this half. So asymptotes of exponential and logarithmic functions. So an exponential function of the form f of x equals a e to the bx for positive b has a horizontal asymptote y equals 0, right? So exponential functions, we have a horizontal asymptote. Exponential function for a e to the bx where b is negative still has y equals 0 as a horizontal asymptote. Log functions have vertical asymptotes, right? Usually it's x equals 0. All right, as long as you don't move it, right? This one's been manipulated. This one has been moved, so the vertical asymptote is going to be x equals a as x approaches a from the right, right? If the a weren't there, if it was just like the log of x, then it would be coming from the right side of x equals 0. Okay. And then if it's reversed, then it's coming from the left. Okay, that's interesting. So here we're asked to find a horizontal asymptote. Let's see. Transformations, do we need to rewrite it? Okay, if we think about transformations, normally, okay, so let me see if I can do my transformations here. We can factor that out. Give me a second, gentlemen. Greetings. I'll be free around 7:30. Yeah, just text me. Okay. Let's see. Horizontal. Okay, that's fine. Okay. So with this guy, right? So for the horizontal asymptote, we're concerned with basically as the absolute value of x gets really large. Let's just focus on as x goes to positive infinity, right? So what we're gonna do, let's start by getting a copy of the original. We have this f of x equals, now bottom we have 1 plus 25 e to the 0.04x under 200, okay? Now we got that negative exponent. So let's rewrite that. So that's the same as 25 over e to the power of 0.04x, okay, under 200, okay? So now let's consider the limit as x goes, let's just focus on positive infinity for right now of what we have, right? This e to the 0.04x under 25 under 200, right? So now as x goes off to positive infinity, as x goes off to positive infinity, this guy gets really big, which means, so the denominator goes to infinity. So then you have a fixed number over a really large number. So then what that means is that this guy tends to 0. Okay. So it looks like as x goes off to positive infinity, what is that, 200, right? Because it's going to be 200 over 1 plus 0. So it looks like it approaches 200. Let's think about if we did as x goes off to negative infinity. If that were a negative, what would happen? Would it tend to 0? If this were going off to negative infinity, then this guy flips, right? That flips. So then that causes this denominator to go to infinity, right? If we flip this guy and let x run, then the denominator goes to infinity, which means the whole expression tends to 0, right? So let me write that. So the limit as x tends to negative infinity. So if that's a negative there, it should flip here. We're going to have this 1 plus e to the 0.04x under 25 under 200. My claim is that, again, the denominator essentially expands to infinity. So that means that the whole expression tends to 0. So I'm going to say this guy approaches 0, right? So as we go off to the far right, it looks like we get closer to 200, but as we go up to the far left, it looks like we approach 0. Right, so we might have 2 horizontal asymptotes. This looks like a logistic.
Professor,
Go ahead.
can you explain the limit as x approaches negative infinity that the whole function equals to 0 again?
Yeah. Okay, yeah, I'll do it. Give me just a moment. I just want to confirm that this is great. Yeah, this looks good, right? So we got it here, we got it here, right? Okay, let's fix it. So I'm assuming that like the 200 one is okay. That one I guess makes sense. So then let's copy. So for the other one now, what you got to do is you think, okay, you know you have a negative here. This exponent is negative. Right? When as we go further and further to the left, the exponent is negative, right? So what I was doing in my mind was like, okay, if it's a negative exponent, I just flip that fraction. So the limit, this guy here is going to be the same as the limit as x goes to infinity of, if we flip that guy, it's going to be e to the power of 0.04x over 25 plus 1 under 200, right? So going to negative infinity is the same as this guy going to positive infinity. Does that make sense? I just addressed that negative. And then once I address the negative, so now this guy is going to infinity, right? Remember, it only goes to 0 if we have a fixed number. Like if this were flipped and we had a fixed number over infinity, then that would be 0. But the reverse basically runs to infinity. So as x goes to infinity, this guy gets really, really big. It goes to infinity. So infinity over a fixed number is still infinity, right? So this guy expands to infinity, which forces infinity, basically infinity plus 1 is still infinity. I know it's a little bit weird, right? I don't know how to say it another way. But because that expression flipped, the whole denominator goes to infinity. It doesn't collapse, right? So now if the denominator is running to infinity, so now we have a fixed number over infinity, which is the stipulation for it to run to 0. So again, because we have a fixed number over essentially infinity, then that tends to 0. Whereas in the previous one, again, this guy went to 0, so we had a fixed number over 1, and that's why it was 200. Hopefully that's okay. Okay. All right. Okay. Let's keep going. All right, let me see what they say. So as x goes off to the right, y. Oh, is that the second? Let me see. Okay, here. Let's look at here. So the limit as x goes to infinity of, is that the original? Yeah, right? The limit as x goes to infinity of the original, remember, here it is, right? Again, this guy collapses to 0. So then 200 over 1 plus 0 is 200. So that was as x goes off to the far right. Now as x goes off to the far left, see this guy blows up or expands to infinity. So then essentially what that is, this is infinity as well. So a fixed number over infinity is 0. So that's how we got these two results, 200 and 0. Okay. And here's a graph of that situation. Going off to the far right, it approaches 200. Going off to the far left, it approaches 0. Okay, that was interesting. Okay, we got a little bit of time. Let's keep going. Let me see. So the strategy for sketching graphs. So I think we kind of touched on this. So we're going to add some parts to what we did before. First, we want to investigate any intercepts and then any asymptotes. Look at the derivatives in the domain, any critical values, whether the function is increasing or decreasing, any points of inflection, I think that's it. And concavity, right? And then put all those pieces together. That's a lot, right? So it's not difficult, and you know all this stuff. You just got to take it part by part, right? So again, let's recap that. The strategy for sketch and graph. First, we're going to investigate any intercepts. You know how to find intercepts. We're going to go ahead and find our derivatives in our domain. So that we have to like throw any x values out. Go ahead and values from our first derivative. Okay. The first derivative tells us whether the function is increasing or decreasing. We can get max and min from there. The second derivative tells us the concavity, and when the second derivative is 0, that's where our potential points of inflection are going to be. Okay. Again, the second derivative tells us about concavity, and then we put all those concepts together. Okay, we're going to do at least one of these guys, and then we'll move on to the next section. Right. So here we're asked to sketch the graph of this guy. Okay. So let me try to write out the game plan again. Literally what we just said. All right. So our first thing that we're going to look at, we're going to find any intercepts. Okay. So there's x-intercept and y-intercept. Or I would recommend do the y-intercept first. And then for the x-intercept, we would set the numerator, and then they did derivatives, I think, next. Asymptotes. Okay, cool. Yeah, that's what I was thinking. Okay. So then after intercepts, we're going to find our asymptotes. Then we'll find any derivatives. Well, we'll investigate increasing or decreasing and max and min. Okay. And then we'll investigate, I'm going to abbreviate this. This is like concave up. That's how I draw concave up, and concave down. And then inflection points. And then A, B, C, D, E, F. Yeah. And then the final one is sketch the graph. Sketch the graph. Okay. So this is the game plan. This is what we're going to be attempting to do. Okay. I'm definitely going to need some space here. So let me go seamless, and hopefully my battery is like, it's kind of struggling a bit. I'm gonna just kind of go with it. I guess I should plug it in, but I'm gonna kind of go with it for now. Okay. Let's start by getting a copy of the original. So we have f of x equals x squared minus 4 under 8. Okay. So our first goal is we want to investigate any intercepts. And I would recommend start with the y-intercept first. That one often is easier, right? And to find the y-intercept, we set x equal to 0. Okay. If we set x to 0, then the y-intercept. Okay, I'm just trying to wrap this one up. This is going to take a little while. If we set x to 0, what do we get? -2. So that's a y-intercept. Okay. If we can find the y-intercept, we can talk about the x-intercept. Now, for a rational function, the x-intercept, what we do is set y to 0. So this guy is going to be equals to 0 when the numerator is 0. In this case, the numerator is never going to be 0. So no x-intercept. All right. So x-intercept, we would, in this case, I'm going to abbreviate it as n of x, set the numerator to 0. It's really set y equal to 0, but because it's rational, it's really the numerator. Right? Okay. But in this case, the x-intercept, we have none. Okay. And I'm going to highlight it like this. These are our results. Okay. So then if we can set the numerator to 0, that means we can set the denominator to 0. Right? So that's going to give us information about any asymptotes. Okay, so let's start off with the vertical asymptote. Notice that what we have difference of squares, so plus or minus 2. So then basically is x equals plus or minus 2 are vertical asymptotes because they both make 0 in the denominator. So those are vertical asymptotes. So then let's investigate horizontal asymptote. Okay. So for the horizontal, we compare the degree of the numerator to the degree of the denominator. The degree of the numerator is less than the degree of the denominator. So the horizontal, let's put it in low power. Let me just plug it in. I don't even know why. I won't just plug it in. I guess I'm just like being a little bit like adventurous, but I don't want it to cut off on you guys. So let me, and sometimes when I plug it in, it still doesn't charge enough to stay on. So let me just plug it in. So the horizontal asymptote, the degree of the numerator is less than the degree of the denominator. So a horizontal asymptote should be y equals 0. Right? Again, if you let the limit, take the limit as x goes to plus or minus infinity, we're going to have a fixed number over infinity, which is essentially 0. Right? So that's why that's the result there. Okay. So then the next goal is let's investigate, let's find our derivatives. Okay. So if we're going to find our derivatives, let's start with, let me get a copy of the original. Okay. So we got this f of x squared minus 4 under 8. So we can write f prime here. I don't feel like doing that. We need to do quotient rule, right? Bottom, low D high minus high D low over low low. Okay, let's just do it. We could rewrite it as a negative exponent, but let's just do the quotient rule. So bottom. Oh no! Ooh, okay, I thought it was about to die me. It went black. Okay, anyway, let's keep going. So the first derivative, the bottom, which is this guy, times the derivative of the derivative of the top is 0, right? So that's all gone. The bottom times the derivative of the top minus the top. The derivative of the bottom is going to be what? Just 2x, okay? All over the bottom squared, which is x squared minus 4 squared. And again, this term goes to 0. So then the first derivative, our f prime, let me move this. I thought it was going to be faster. Let's move it here. So then our f prime is going to be, what is that? A negative 16. I'm going to leave this as x squared minus 4 squared under negative 16x. Okay, so that's our first derivative. Let's go ahead and find a second derivative as well. All right, so let's do the same thing. Low D high. So the second derivative, so the bottom, which is this guy, x squared minus 4 squared, times the derivative of the top is going to be a negative 16 minus the top, which is this negative 16x, times the derivative of the bottom. So we got to use the chain rule. 2 x squared minus 4 times 2x. Okay, all over the bottom squared, which is x squared minus 4 to the power of 4. Okay. Negative 16, we can factor out a negative 16. Okay, and they both have the x squared minus 4. So we have some, let me try to highlight my like terms, right? They both have at least one of these x squared minus 4s, at least one negative 16. Again, here's a negative here. Let me back up. So they have this, and then x squared minus 4. Okay. Okay. All right. So both terms have that guy that we can factor out. Okay. So if we keep going, I'll just work here. So then f double prime. So let's factor out the like terms, like factors or whatever. So we can factor out a negative 16 times x squared minus 4. Now, if we take that from the first term, we're going to be left with x squared minus 4. The negative 16 is out. And the second term, what is that? 2 times 2 is 4. So it looks like a negative 4x squared. And I think that's all that's left in the second part. And then it's still over. And again, it's like this because we factor. We still have this x squared minus 4 to the 4, right? So then what happens is one of these cancels, turns this into a 3. Okay. Okay, so our second derivative that we get this, hopefully I haven't made any mistakes. It's very easy to make a mistake in something like this. We can combine like terms there. So 1 minus 4 is a negative 3. It looks like we could factor out a negative. If we're getting a negative 3x squared, let's just factor out that negative. It's going to cancel this negative. So then it looks like we're going to have 3x squared plus 4 over x squared minus 4 cubed. Okay. All right, so that's our second derivative, right? I kind of want to put these side by side. So let me get a copy of, I want a copy of this, this. Let's copy. Okay, that took a little bit of effort. So we got our F there. I'm still trying to get to my other section. We're just gonna have to do the best we can. Here's our first derivative. Hang on, let me just try to wrap it up before questions. And then our second derivative is x squared minus 4 cubed. Unless, do you make a mistake? If you see a mistake, then we'll stop. But if you don't see a mistake, let me just try to finish this. Okay, so we got our original, we got our first derivative and second derivative. Okay, so we got our derivatives. So then the next so let's talk about max and min from the first derivative. So that was 3. So then part 4. I think I'm gonna need another page. Okay. So then 4, I'm just gonna say increasing, decreasing, and then max, min. Okay. So for the critical values from the first derivative, the critical values are going to occur when the first derivative is either 0 or undefined. So in other words, any x that makes either the numerator or the denominator 0 are candidates. So looking at the first derivative, x equals 0 makes the numerator 0. X equals plus or minus 2 makes the denominator 0. Okay, so those are our critical values that we want to test. Okay. So, all right, we're going to put those on a number line. We said what, 0? And then I think it was plus or minus 2. Okay. Okay. So, and we're really just considering f prime of x right now. Now, that's going to be a 0 in our first derivative, and these guys are going to be basically vertical asymptotes, or they're going to be undefined. So these 3 candidates for critical values break the number line up into basically 4 regions, right? We have this region A, region B, region C, and region D. So what we need to do is choose points in each of those regions to find out if the original function is increasing or decreasing. So for instance, in region A, when x is negative 3, if we plug negative 3 into the first derivative, double negative is going to be positive. If that's what, a negative 3, 9, that's going to be a positive. So a positive divided by positive. So it's going to be, in region A, the first derivative is going to be positive, which implies our original function is increasing left of negative 2. Let's choose something in region B, something like negative 1. If we plug in negative 1, this is going to be a positive, right? This is going to be positive. If that's a negative, so it should be positive in region B, okay? Hopefully I haven't made any mistakes, all right? So that means that negative 2 is not a relative max or min. Let's choose something in region C. Let's choose when x is 1 and plug it into the first derivative. When we plug 1 into the first derivative, we get a negative on top, and a positive on bottom. So then ultimately a negative divided by positive is negative. So it's decreasing. So that means that 0 is a relative max, right? Because the function goes from increasing to decreasing. Let's choose something to the right of 2, namely 3, and we should be able to anticipate it, right? So this is going to be if that's a 3, yeah. This is going to be a negative. This is going to be a positive. Negative divided by positive is negative. So the original function is decreasing. So we only got one extrema. When x is 0, we need to find the corresponding y. So when x is 0, going back to the original, I think the corresponding y is -2. So we have a relative max. What color did we use? I think we used purple before. Yeah. I know it's a lot. I don't know about, we're gonna do the best we can with this other section, right? This is why I make my pre-recorded videos. Okay, so that was increasing, decreasing, max and min, and critical values, right? Okay, so we only had one critical value, one relative max at the point 0, -2, okay? Let's see. So then we have points, inflection points and concavity. So we need to look at the second derivative. So concavity, I'm just going to say like concave up, concave down, and points of inflection. Okay. So in other words, we need to look at the second derivative and get any critical values from the second derivative. If we set that numerator to 0, we get a funky number. Let's see, if that's a parabola, it's opening up, we move it up, right? So we're not going to find an x that makes the numerator 0, right? Because even if you set it to 0, divide both sides by 16, subtract, divide, x squared equal to a negative something, right? Yeah, so we're not going to find an x that makes the numerator 0. But I think we could find some x's that make the denominator 0. Plus or minus 2, right? Okay. So we get two critical values plus or minus 2 to test in the second derivative. So here's -2, here's +2. Just hang tight, guys. I know this is intense, but I just want you to see. Okay, plus or minus 2, right? So when we plug in plus or minus 2 into the second derivative, let me think. Do we need to plug it into the first derivative? No, because it's not defined there. I think they're just undefined, right? It's because you still get your 0 in the denominator. So I think it's no points of inflection. Let me think about it one more time. Yeah. Because we got vertical asymptotes at, let me see, vertical asymptotes. Yeah, plus or minus 2. I'm going to say no points of inflection, right? Because from that second derivative, we get 2 that are undefined, but okay, here. Let me test. Hang on. Let me do this. So if we're looking at the second derivative, again, it's undefined there, it's undefined there. So then if we go to the left of -2, if we plug in -3 into the second derivative, this is going to be positive on top, positive on bottom, right? So positive divided by positive is positive. So what this means is the second derivative is positive, which means that our original function is concave up, left of -2. Let's choose a number between -2 and 2, which is going to be 0. If we plug 0 into the second derivative, let me see, this is going to be positive. This is going to be negative, right? So positive divided by negative is negative. So the second derivative is negative between these two values. So that means the original function is concave down. To the right of 2, let's choose 3. If we plug in 3 into the second derivative, this is positive. This is positive. So the original is going to be concave up. Concave up, right? Okay. So it looks like, but I think that the original, those would be points of inflection, but I think the original is not defined for plus or minus 2. So this just tells us about concavity, but we don't have any points of inflection. We don't have any inflection points, but it does go from concave up to concave down because of the asymptotes. Okay, we're going to see this in just a moment. Okay, so I think the last thing is put it all together. Sketch the graph, right? Okay, so we're going to put all this together. Home stretch. Let's finish it. 6. We want to sketch. Okay. All right. So I'm gonna well, I guess I can do some graph paper. Go to templates. Like this. One is fine. Apply. Okay. I'm just gonna kind of. I'll adjust things as needed. I'm just gonna kind of do a rough like that, and then like this. Okay. This is my positive X in this direction. This will be my positive Y. I'm going to kind of zoom out some just to kind of see a little bit better. Okay, so my X's, okay. Here, Y-intercept, we got a Y-intercept of 0, -2. So let me see. So for my tick marks, so it was going to take a while. We're going to do the best we can. I know we're almost out of time. Let's see. Let's go like this. Just let this be a 1, 2, like that. Actually, let me change it up. I went too far. Undo. Okay, let's go like this. Let's go 1, 2, 3, 4, 5, 6. And we'll just kind of go like that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It's probably a little bit far, but that's okay. 1, 2, 3, 4, 5, 6. This is the origin, and we counted this as 1, 2, 3, 4, 6, 7, 8. 2, 3, 4, 5, 6. 6. 6, negative. All right, so now let's just take it part by part. I'll do these in blue. So the first part we got was the Y-intercept was 0, -2. So let's put that in there. 0, -2 is here. So this is the point 0 here. So point 0, -2. Okay. I think we had no X-intercepts. Let me look at it again. So that was that one. We had vertical asymptotes at ±2. So let's capture that. Okay. So what I'll do right here. Okay, that looks good. Style. We can make it a little bit thick, about like, that's pretty good. Okay. And let's copy that guy. We're going to paste it right here. Come on. Okay, right. So there's our vertical asymptote. So this is basically, this is X equals 2. This is X equals -2. All right. There's our vertical asymptotes. Okay. So the next part, we had a horizontal asymptote of Y equals 0, which is basically the X-axis. Okay. So what I'll do for that, I'll go kind of like this. Okay, that's good. Let's go style. We want it to be thicker, about like that, I guess. Dash. And that's a horizontal asymptote, Y equals 0. Y equals 0. Okay. So we got our verticals, we got our horizontal, we got our Y-intercept, no X-intercept. Okay. We did the vertical and horizontal. Okay, so the derivatives that told us about increasing. Now, we said that it's increasing left of -2, and also left of -2, we said it was concave up, right? So one other part was a few additional points. We should have chosen points between and beyond our vertical asymptotes and x-intercepts. In other words, what I'm saying is choose points basically like here in this region, just choose an x here. Choose something choose a few x's here and choose something here. But if we put it all together, for instance, like if x is -3 into the original, would that be simple? If that were -3, 9 minus 4 is 5. So if that were 8 divided by 5. Hey Siri, what's 8 divided by 5?
8 divided by 5 is 1.6.
Right. So when x is -3, the corresponding y is approximately like 1.6. So it's basically in the upper region, -3, 1.6. So to graph this, that's basically telling us all it is happening is, right? You can choose several values of x, find the corresponding y. But when you go to graph it, when you go to sketch the curve, it's saying, okay, we're starting in this upper left-hand region. So all we do is start close, right here. Start close to the horizontal asymptote, pass to whatever points are here, and then finish close, right? Again, we pick points that tells us the region we're in. Again, we would choose additional points here, but all we're doing is starting close to this asymptote, passing through this point, finishing close to the asymptote, right? And then if you chose like 3, it should be in this region. Start close to the asymptote, pass through your point, finish close to the asymptote, and that's the gist of it. Okay. All right. That took way longer than I would have liked, but that's just, I don't really know any other way to kind of go about that. That's just what it takes. You just have to, all those parts together come together like this, right? Let's do a quick recap. Okay. We found our intercepts, right? You know how to do that. We found our vertical asymptotes, horizontal asymptotes, and or slant or oblique asymptotes if there are any. We took the original, we found the first derivative and the second derivative. You saw the effort that we put there, right? We had to do quotient rule twice. Then we used the first derivative to investigate relative max and min, right? We found one relative max. You see how it looks, right? It's increasing left of -2, decreasing right of -2, and 0, -2 was a local max, a relative max, okay? And then we use the second derivative to investigate concavity. You can see that left of -2, the graph is concave up, the cup opens upward. Right of 2, the cup opens upward. Between -2 and 2, the cup opens downward, right? So, I mean, sometimes it's just inescapable, right? It's just inescapable. I partly want to be like, the concepts are simple, but it's definitely information overload, right? And it's very easy to get intimidated by this. Let me see. I'm just trying to, pull up the graph at least. Okay. And you see here's and so once we had all those, the other thing was basically choose a few additional points, So where I just kind of did a rough sketch, you can choose a few additional points and then, and it should fit all of those things that we talked about. You just have to take your time, take a deep breath, be confident, know that you can do it, okay? Now we have just under 15 minutes. I want to take the remaining time to just touch on the next section. Again, these presentations are recorded. Let me go ahead and make a copy of this available. We almost finished this section. But let me go ahead and make a copy available because I definitely wanted to go through that curve sketching. Like I wanted to do at least one demo on that. Notes, handwritten notes. It's in it there. Okay. So you'll get a copy of my notes for 3.3, and we're just going to touch on 3.4, and I have to rely on my my recorded lecture, right? Again, now you're starting to see, we don't have enough time together to kind of go through this stuff, so that's why I went out of my way to make these recordings available in advance, because I have to. Like, that's just what we have to do. But after today, we can at least focus on one section at a time and not be trying to get two in there. All right. Okay, so let's just kind of do a quick scan of 3.4. So now this one is actually you actually know how to do this one. This is similar to what we were doing before, finding absolute finding. It's similar to finding relative max and min. The only difference is the difference between relative max and min and absolute max and min is that relative is like when you're close to a certain point. Absolute is across an entire closed interval. So you also have to test your endpoints. I know there was a question on the previous section. Hopefully you remember it. Just write it down and we can talk about it at the end of class. Right. And let me just kind of scan this a little bit. A few objectives here. We like to find absolute extrema using max and min principle 1, and then find absolute extrema using max and min principle 2. So suppose that f is a function with domain I. F of c is the absolute max and min if f of c is less than all corresponding y for all x in the closed interval I. F of c is the absolute max if f of c is greater than or equal to all corresponding y for all x in the closed interval, right? So min basically is less than any y value on that closed interval. And absolute max is f of c is larger than any y value on that closed interval, right? That's all this is saying. So the extreme value theorem, it says a continuous function f defined over a closed interval AB must have an absolute max value and an absolute absolute minimum value over the closed interval, right? So whenever we're doing absolute max or absolute min, you have to talk about it over a closed interval. Okay. So suppose that f is a continuous function defined over a closed interval AB. To find the absolute max and min values, first find the derivatives, then determine all the critical values on that closed interval. And then, so the critical values occur where the derivative is either 0 or does not exist, right? So those generate our candidates for the critical values. So then we list the critical values along with the endpoints A and B, the endpoints of the closed interval. So then once we have our candidates for the critical values, and we have those endpoints, then we basically just pass all those values to the original function. And then whatever produces the highest y value is your absolute max. Whatever produces the lowest y value is your absolute min. Okay. So here we're asked to find the absolute max and min of this function over the closed interval. That's weird. From -2 to 3/2. Okay. So again, to do this one, first we find the first derivative. So we're going to say f prime is going to be what? 3x squared minus 3. Okay. So then the critical values are going to be where this is either 0 or undefined. This is never going to be undefined. So we're going to find the x's that make this guy 0. If we add, we're going to get what? X squared equals 1. So then x equals plus or minus 1, right? So then to find the absolute max or min, we can basically make a table. X versus f of x. So the endpoints, we have -2. The critical value was -1 and 1. And then 3/2. So then we basically going to find the corresponding y. I think I'm going to use my trusty dusty rusty. All right. Like this. That's going to have to be good for right now. This one. Okay, we'll hang out for like 5 more minutes. Okay. Reload and refresh. Okay, and the original, we got x to the power of 3 minus 3x plus 2. Okay. So we just want to find the corresponding y's. Oops. So when x is -2, the corresponding y is 0. When x is -1, the corresponding y is 4. When x is 1, the corresponding y is 0. And then when x is 3/2, corresponding y is 0.875. Okay. So from there, the highest one, this is our max. The lowest one, so it looks like we have 2 minimum values. Okay. And those are all ordered pairs. Okay, we're going to go with that. Let me wrap this up. So the absolute max value, is 4, which occurs when x is 1. The absolute minimum value is 0, which occurs when x is 1 and 2, right? Okay, let me just try to scan. Quick check. I'll leave those for you guys. So the maximum minimum principle 2, suppose the f is a function such that f prime exists for every x on a closed interval, and there is exactly 1 critical value on the interval, then the absolute maximum value over I is going to be when the second derivative is negative, or the absolute min if the second derivative is positive, right? So if you get a closed interval and you only have 1 critical value, then you can look at the concavity. If it's concave up, that's going to be the absolute minimum. If it's concave down, that's going to be the absolute max. So maximum principle 2 is if, again, the caveat there is if we have exactly 1 critical value on the closed interval, okay? I'm going to have to leave the rest to you, okay? These should be in my recordings. If they aren't, or if anything is off, just let me know and I can fix it. And hopefully you guys are working together, working with the tutors. I know there's at least one student that is like consistently working with me, so I know at least one student is getting it there. You know, you guys just have to do the best you can. I'm here. I can meet in person. I'm in Dansby 201. I'm usually there in the mornings, like before 8. My official office hours, I think I said it for like Tuesday and Thursday, 7:30 to 9, and Dansby 201, right? Okay. Okay. Would you guys like to ask any questions? I know there was a question earlier. I don't know if you want to try to ask it now before we go our separate ways. Okay, let me send a copy of this. Okay. All right, so when this bar finishes loading, you will get a copy of everything that you saw me writing. Like, don't be intimidated by this stuff. I know what it looks like. You know, don't be intimidated. Like what it is you just have to like take a deep breath, right? So keep in mind you have a cushion, you have some things in your favor. Keep in mind, with all the assignments, you get unlimited attempts. You're not in a testing environment, right? So like just, you know, the real intent of this structure or setup, I'm really just trying to introduce these concepts to you guys and encourage you to think about them, right? I'm not trying to go hard. I'm not trying to discourage you. I'm just trying to get you to take a deep breath, to slow down, and to try. Honestly, I feel like if you just try and push a little bit, I think you'll be okay. Because on my end, I'm just looking for whatever's on Pearson. You get unlimited attempts, right? So and the main thing is if you're trying to maximize your score, you want to prioritize your exams, right? I know we only have 2. We've only had 1 so far. But that's where the bulk of your points are going to come from. The homework and quizzes are really just there to get you ready for the exams, right? Each question in the homework comes with a view and example. It comes with an explanation. You guys can team up with whoever you're comfortable with. If you're not comfortable working with me, you know, I'm not for everybody. I'm just here as a guide to try to encourage you and point you in the right direction. If you can tolerate my energy, then, you know, I'm here, right? That's what you guys are paying me for, to help you with this. But if you can't get it from me, maybe you have a classmate that gets it on some level that you can work with, or the tutors. The tutors should definitely be able to help you. We definitely, and you've already paid for the tutors as well. They're included in your tuition. With that curve sketching, I tried to break it down to the most simplest components as best I could, right? It was the 5 concepts. First, we had the intercepts. Then we had any asymptotes. Then we looked at the derivatives. Then we found like max and min. Then we found inflection points. Then we plotted a few additional points and basically put all those concepts together, right? You just have to take it part by part. Don't think about the whole thing. Just break it into digestible pieces, okay? All right. Are there any questions? Again, final call for questions. Going once, going twice. Okay. All right, gentlemen. So if there aren't any burning questions, we're going to go ahead and... Yes, go ahead.
Is this going to be in your recordings?
Yeah, it should be. It looks pretty good. I do need to go and update the thing. You should be able to find it on my channel. I just need to reorganize it. It might not be in my playlist right now, but it should be on my channel. All the recordings should be there because I'm streaming directly to my channel. I just need to go back and move stuff around so that it's easier to find. if you're not able to find, I mean, they're all there. And I do intend to kind of put them into that playlist. I just haven't done it yet. But you should be able to find these on my channel. Like if you go to my channel and go to videos and put it in order of upload date, you can find it that way as well. Okay.
Okay.
Any other questions, gentlemen? All right. So just shake this stuff off, rest, eat something, you know, just zen out for right now. Go to sleep. I would encourage you to go to sleep. And then whenever you wake up, that's what I used to do. I would just go to sleep. Whenever I wake up, whatever hour, that's when I would start focusing. Whenever I first wake up, that's when my mind is the most clear for me to process this kind of information. If I try to do it at the end of the day when I'm tired and all this other stuff, I don't have my focus, then, you know, nothing gets through. Okay. All right, guys. If there aren't any other burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, guys? Take care. Peace. All right.